Kotlin Desktop. Lesson 19, Performance and Profiling. Today we build a performance lab that visualizes compose recomposition with live metrics. Here's the app we're building. A product catalog with 200 items, search, sorting, and a real-time ticker. A toggle switches between naive and optimized implementations. The MetricsPanel on the right shows live recomposition counts, color-coded by severity. In naive mode, the ticker cascades recompositions across every card. In optimized mode, 5 fixes keep counts minimal. We start with a new Compose desktop project called Performance Lab. The settings file sets our project name. The Gradle wrapper ensures everyone uses the same build tool version. Kotlin 2.1, Compose 1.7.3. Standard dependencies for Material 3 and icons. The Compose block sets our main class. Source directory created. Now for our data models. Product models defines 2 versions of our product data class. First, a plain data class called product. Notice the var for isFavorite. This is our naive model. Compose cannot guarantee stability. Next, stable product annotated with @immutable. All val properties. Compose can safely skip recomposition when the instance has not changed. Sort order enum defines our 5 sorting options, and a stable converts between the 2 product types. Now the product data generator. This creates 200 sample products across 6 categories. Categories, adjectives, and noun maps combine to produce unique product names with deterministic prices and ratings. "200 products with realistic variety. Enough volume to make recomposition differences visible." Now the recomposition tracker. This is the measurement tool that makes performance differences visible. We import side effect from Compose and concurrent hash map with atomic integer for thread-safe counting. Recomposition tracker is a singleton object. Track increments an atomic counter for each named composable. getAllCounts returns a snapshot. Reset clears everything. Track recomposition is marked non-restartable composable, so compose never skips it. The side effect inside fires after every successful composition, making it the perfect hook for counting recompositions. Now the metrics panel. This displays the live recomposition counts. A launched effect polls the tracker every 500 milliseconds, updating the displayed counts. The card shows a header with a reset button, a total count, and a sorted list of composable names with their individual counts. Metric row uses monospace font for clean alignment. Each count is color-coded: green below 50, orange between 50 and 200, red above 200. Simple color thresholds make the difference between naive and optimized immediately obvious. Now the naive implementation. Shared components first, with a search bar used by both modes. Search and sort bar takes search query and sort order as parameters with callbacks, a text field for search, and an icon button that opens a drop-down menu for sorting. The drop-down shows all 5 sort options with the current selection in bold. Category color maps each product category to a distinct color for visual grouping. Now, naive product list. This is where we intentionally demonstrate 5 common anti-patterns. Anti-pattern 1. The ticker count is read directly in the parent body. Every 500 millisecond tick forces the entire composable tree to recompose. Anti-pattern 2. Filter and sort run as bare code. Since tick count changed, this entire block re-executes every tick, even though search and sort have not changed. Anti-pattern 3. Items with just the size parameter uses positional matching. When items shift positions after sorting, Compose cannot reuse existing compositions. Anti-pattern 4. OnFavorite creates a new lambda instance every recomposition inside the loop. This prevents Compose from skipping unchanged cards. Now, naive product card. It takes the unstable product class. Anti-pattern 5. String.format runs every recomposition to format the price. No caching, no remember. The card layout shows a color indicator, product name, category, star rating, price, and a favorite toggle. Every single card recomposes on every tick. Five anti-patterns in about 90 lines of code. Each one compounds the recomposition cost. Now the optimized version. Same functionality, 5 targeted fixes. Fix 2. The filter and sort logic is wrapped in derivedStateOf inside Remember. It reads search query and sort order, but not tick count, so the ticker cannot trigger refiltering. Fix 4. The onFavorite callback is wrapped in Remember. Same lambda instance across recompositions, allowing compose to skip unchanged cards. Fix 3. Items now takes a key function that returns the product ID. Identity-based diffing means compose can reuse compositions when items are reordered. Bonus fix. Ticker display is an isolated composable. Only it recomposes on tick changes, not the entire parent tree. Now optimized product card. Fix 1. It takes stable product, our @immutable data class. Compose trusts the stability contract and can skip recomposition entirely. Fix 5. The price format uses remember with the price as key. The string is only formatted once and cached until the price changes. Same visual layout as the naive card. Same features. But the recomposition count drops from hundreds to single digits. Five fixes. Each one addresses a specific cause of unnecessary recomposition. AppContent ties everything together with a mode toggle. Lab mode enum defines naive and optimized. Products are generated once with remember. A segmented button row in the top app bar switches modes. Each switch resets the recomposition tracker for a clean comparison. The content area uses a row. The product list takes weight 1F on the left, and MetricsPanel takes a fixed 280 dp on the right. Main. KT is minimal. A single 1100 by 700 window with dark theme. Let's compile and see the performance difference in action. Here is the app in naive mode. Watch the recomposition counts climb rapidly. Hundreds of recompositions in seconds. Searching for premium filters the list. But counts keep climbing because every tick refilters all 200 products. Sorting by price resorts on every tick too. The entire tree recomposes every 500 milliseconds. Switching to optimized mode. Counters reset. Notice how much slower they climb. Same search, same sort, but derivedStateOf means filtering only runs when the search text changes. Resetting counters shows the difference. Naive climbs fast. Optimized stays at single digits. Let us recap 5 key takeaways. First, at immutable and at stable. Annotate data classes so Compose can skip recomposition. Second, derivedStateOf. Wrap computed values to recompute only when inputs change. Third, key in LazyColumn. Pass unique IDs for identity-based diffing. Fourth, remember lambdas. Extract callbacks with remember to avoid new instances. Fifth, isolate volatile state. Put tickers in their own composable to prevent cascading. Thanks for watching. Like and subscribe for more Kotlin Desktop tutorials.